Lightning looks random. One moment the sky is quiet, the next moment, a bolt splits the darkness. People ask one question: why that exact spot? Lightning is not purely random. It follows rules. Those rules come from charged air, ionization, and current finding a path that can carry charge. So don't zoom in like a magician. Zoom in like a detective. Start with the conditions. Inside thunderstorms, charge separation builds. Updrafts and downdrafts move ice and water droplets. Collisions separate charge. Often the upper cloud becomes more positive. The lower cloud becomes more negative. The ground can become involved too, mainly through induction. Think of the storm and the ground as an electrical network. Air normally resists electricity. But it is not a perfect wall. As the electric field strengthens, it pushes electrons into motion. Small pockets of ionization form. They are like sparks testing the sky. Now the key idea. Lightning begins with a leader. A leader is a thin, branching channel of ionized air. It does not grow smoothly. It advances in steps. Each step matters. The leader moves from easier ionization to easier ionization. It creates a temporarily conductive area. Then it waits for the next set of conditions to jump again. Why the steps? Because the leader must ionize new air at the front. That takes power. It charges the surroundings, then it pauses, then it advances again. Branches can also appear. Multiple routes may become partially ionized at once. They compete. The branch that maintains the stronger electrical connection tends to keep growing. Think of the leader as exploring. It searches for a route that can support continued current flow. While this happens inside the storm, there are scouts on the ground. Tall objects respond to the storm's electric field. Trees, towers, and buildings can concentrate the field at their tips. That can launch upward moving streamers. In the sky, the descending leader is still stepping. Lightning does not fully commit until it bridges the gap between the leader and the upward streamers. So what decides which connection wins? The charged air and the flow of current. The electric field controls voltage across distance. A stronger field accelerates electrons more easily. Collisions create more ionization. More ionization means lower resistance for the next leader step. This creates feedback. As the leader progresses, it heats the air and increases conductivity along its channel. When current starts to flow, the channel can widen and brighten. The route that supports the strongest, most sustained current becomes the main stroke. Branching can continue too. Channels can split or shift as different branches find better electrical conditions. Here's the crucial concept. Current chooses the path. The atmosphere provides candidate routes through geometry and local conditions. Ionization opens doors. Then current flows and rewards the route that can carry charge most effectively. That's why lightning often seems to hit one specific point, like a tree or a roof. That point often has a stronger electric field and a higher chance of connection. Ground objects differ in height, shape, and conductivity. Those differences affect where upward streamers can rise and where the descending leader can link. Even the surroundings matter. Wet soil can conduct better than dry soil. Metal fencing can provide extra pathways. Uneven terrain can create local peaks in the electric field, and storms change fast. Charge distribution and electric fields can shift in seconds. Timing is everything for the final gap closure. The descending leader and upward streamers must coordinate. If conditions change before they meet, the connection can fail. Then the strike may pivot to another route. Here's one more detail about the leader. Each step needs ionization maintained at the front. The newly ionized region becomes a conductive bridge for the next leap. If a branch reaches air that can't support further ionization, it fades. If another branch finds a stronger electric field or more favorable ionization, it keeps growing. That selective growth explains the probing look of lightning. It explores multiple routes until one can sustain the final connection. Then comes the final chapter, the return stroke. Once the leader connects with the ground, voltage drives a massive surge of current back through the ionized channel. That surge creates the bright flash. The channel heats the air rapidly. Heated air expands and generates shock waves. Those shock waves are thunder. The return stroke follows the established channel because it is already ionized and conductive. It is like using a pre-built electrical highway. So when you ask, how did it choose that path? The answer is a chain of cause and effect. Charged air sets up strong electric fields. Those fields enable ionization and let a stepped leader grow. The leader explores branching routes, and the routes that sustain current gain the advantage. Ground objects can accelerate the connection by launching upward streamers and concentrating the field. When the leader and ground connect, the return stroke races along that conductive channel. Lightning is still surprising, but it is not guesswork. It is structured by physics, by geometry, and by changing electrical conditions. Final lesson: the sky may seem chaotic, yet it follows pathways of charge. Lightning chooses a route the way electricity always does, where air can become conductive and where current can keep flowing. So the next time you see a bolt, remember this: it is not guessing. It is negotiating with the atmosphere until the electrical network agrees on a path.